This is a walkthrough of the 2024 GCSE Physics Paper 1 paper for AQA. You will need an equation sheet to help you do the equation questions and also a calculator, pencil and ruler. And it's better to use this video once you've done the paper so you can then self-mark your answers. And I'll try and explain as best I can as we go along. So let's have a look first of all at question 1. We've got a wind turbine. It gives us a bit of information about them, two methods that can be used to store the energy, either heating water to a high temperature or pumping water uphill. So we've got to look at which energy stores increase when the water is heated. So anything that's heated is going to be an increase in thermal energy. The mark scheme also allows internal energy for this and actually also allows kinetic energy, because you could say the kinetic energy of the particles increases. When the water is pumped uphill, there's only one answer for this one, which is gravitational potential energy, which means anything that's getting higher is going to have a greater GPE. It does actually allow, saying that, I've just seen the mark scheme does actually allow kinetic energy, which is a bit of a poorly designed question there, but I say that's the main one you could have here. Next, we've got a 4-mark question, which is comparing these two methods, and we've got some figures here. It says, show the information about, here's the information about the two methods of storing energy. We've got to compare the advantages and disadvantages of the two methods, and we need to include calculations. If you don't include calculations here, you're limiting yourself to 1 or 2 marks out of our 4. So the first thing to talk about would be the sort of obvious advantages and disadvantages of each. Now we can use bullet points here, but we've got to use comparative language. So when it says compare, we've got to say things are better or worse than the other one. So let's start off with method A. So method A says increasing water temperature by 80 degrees. We can see it stores a lot more energy per kilogram than per 100 kilograms than method B. So we can say it says more energy per 100 kilograms than method B. We can also note that actually another advantage of A is that it can be installed anywhere. So you could say it's easier to install than method B. So both of these would be advantages. I don't know why I put D there. Method B. Would be advantages or an advantage. Now I'm going to write an answer that's going to be like even more detailed than you need for 4 marks here. However, we're going to look at some calculations. What could we calculate here? Now we might notice up here we can got the value of percentage of stored energy that's wasted. Now we should know if stored energy is wasted, and we could easily use these to work out the efficiency of both of these methods. So efficiency is going to be the useful energy as a percentage or as a fraction of the total. This is the wasted energy. So we could say actually if 40% is wasted, the efficiency of method A is 60%, because 60% is going to be useful, 40% is going to be wasted. So therefore we can actually work out what 60% of this value is, the energy stored. So we could do, so the total energy stored is going to be 60% or 0.6 of 33,600, which if you set that to a calculator is going to be 20,160 kilojoules. You could even work out how much is wasted if you wanted to. You could say then, okay, 40% of that is going to be 13,440. And that's exactly the kind of thing, when they're after calculations, that's what you can calculate. So to compare the two methods, we kind of need to do like another little calculation. You actually don't need to say this thing twice. You don't need to say B stores less energy or is harder to install, because that's just the converse of these phrases here. But you could say something like for method B, just to do the calculation again, you could say, so efficiency, if we use the same sort of methodology here, 25% is wasted, efficiency is therefore 75%. So therefore we could say total energy stored is going to be 75% of the value of energy stored per 100 kilograms, which is 490. So hopefully you can see here is a lot lower than the other method. So therefore we could say, so it's lower than A. Now, like I said, that's kind of more information you need for 2 marks. But the key thing here is the calculations, because they mentioned that in the question. The last part of question 1.4 seems relatively straightforward, but I've marked a lot of these and you have to be really specific with your language. So we've got decreasing the amount of carbon dioxide released by different activities helps slow down climate change. And we've got transport and generating electricity. It says explain one change for each that would reduce the carbon dioxide released. So we've got to explain it. So we've just got to say one change, then we've got to explain it fully. So transport, I'd say, is the easier one. So we say use more electric cars instead of, so we can't just say use more electric cars. We've got to say what we're doing instead. We've got to say instead of using petrol cars or cars that use fossil fuels. So to explain that, so how do we go about explaining this one? So we normally want to say to reduce CO2 emissions or something like that. However, we don't get a mark for that bit of the question. The mark here is for more electric cars, less petrol cars, because actually they tell us about carbon dioxide in the question already. Generating electricity, we could say use more renewable methods. So you could give an example, you could say solar, you could say wind turbines, whatever. Again, instead of, we use less of fossil fuels or coal, oil and gas methods. And the reason is exactly the same. It's to reduce the carbon dioxide emissions. Like I said earlier, we actually don't get the mark for that here because it says it in the question, but that's absolutely fine. So a lot of people just didn't write down what you're reducing. Make sure you write down, what you're actually doing less of, as well as just what you're doing more of. Let's have a look at question 2. Question 2 is for separate science only, because it's all about nuclear fission, which it tells us in the question. Nuclear power stations, energy is released from, hopefully we can see here, this is a uranium nucleus, so the plural of that is nuclei. So that's the first mark, and it releases these things here. You just need to know this. The process of nuclear fission is that 3 neutrons are released, and the whole point of it is it releases energy. It's an EM wave, which gives us a clue here from paper 2, which is a gamma ray, or in the form of gamma rays. So that's quite a nice fission question. You could be asked that in a sort of 3-mark, 4-mark written answer. Next, we've got our first equation question of the paper, which we're going to look at our equation sheet for. We've got energy, power, and time. There's a couple of ways it expresses it in the equation sheet. You can either use this one here, or we can use this one down here. It's literally the same equation. I don't really know why they're both on the equation sheet, but they are. So you can write the equation, the symbols instead of the words if you want to. E equals P times T. We're trying to find the energy output. To get everything into its right form, we need to spot this bit here. Okay, capital M stands for mega. So megawatt is what MW is here. And a mega is a million, or 10 to the power 6. So when we put that into our equation here, we can't just write 500. We've got to write 500 times by 10 to the power 6, or 500 million. And that's then times by seconds. We don't need to do anything to, because it should be in seconds anyway. So once you put all that into our calculator, we should come up with a nice big answer, but it's a power station, so that kind of makes sense. And don't worry about standard form in answers. It's actually better to use standard form than to convert this into regular numbers at the end. So that's our 3 marks. So 1 for the conversion, 1 for putting the numbers in, and 1 for final answer. One precaution, we need to be careful with the radioactive nuclear waste to reduce the hazard. So not to stop it being produced, but to reduce the hazard. We could say a couple of things here. I would say probably bury the waste deep underground. The idea is that less of it is going to get through the ground. It's all going to be absorbed by the soil and stuff rather than getting to the people. You could say lots of things here. You could say store it in metal containers, cover it in concrete, transport it, lots of different things here. But you need to say 1 for the mark. Next one is an equation question, or a maths question, and we don't need an equation for. We have one nuclear power station generated electricity for 92% of the year. They even tell us how many days in the year, which is really nice. Number of days that it produces electricity. If it produces for 92% of them, all we need to do is find 92% of this number here. So 92% of that is 0.92 times by 365. And if we stick that into a calculator, it gives us 335.8. You can actually either round up or down here. It doesn't say complete day, so I'd probably round up. But 335 is also fine, as well as 336. Question 3, we've got our first required practical question, where it actually tells us all the equipment to use. So we don't get any marks for mentioning any of these, but it's the required practical to do with resistance. So the student plotted a graph of resistance against length of wire. How could they, what method could they use to collect the data needed to plot the graph? So we don't get any marks, like I said, for mentioning this equipment. No circuit diagrams here. You only get marks for actually writing down what you do with it. Now, just from marking loads of these papers, I think the amount of space they give you is quite low here. So we really need to be careful. Number 1, we're using bullet points. Number 2, we're not waffling. We're not saying things like get the equipment together or set up the equipment like in the diagram. So if you have big handwriting, you're going to spend so much space up here, you writing that down, you're not going to have much room to write your answer. Obviously, you can use extra space, but some people don't, and also it's just better to do it on the paper unless you really run out of room. So we're going to look at length first of all. So how do you measure length, which is the most obvious bit because we've got a ruler there. Then we're going to talk about resistance. So like I said, this will probably be too much for 6 marks almost, but I'll write down as many of the points as I can that you could get marks for. So first of all, we're going to write down how to measure the length. So we say something like measure the length of the wire, and that's between the crocodile clips. But we'd say using the ruler, which is a really obvious point, but you want to make sure you get any obvious marks here. So that's the whole point. Then we're going to say, so we're trying to measure the resistance. So all the equipment's set up. You don't need to mention how to connect it or anything like that. We're going to say measure the current using the ammeter, and then the PD or voltage using the voltmeter. And how we're going to use those, if we get our equation sheet back again, is to work out resistance. If you ever forget this bit of the method, the equation is here. So we're going to use this equation, V equals I times R, or we could rearrange it if we want to, but to calculate resistance. So V equals I times R. We don't need to say exactly how to do it. We don't have any values here, but to calculate the resistance, that's the equation we use. So next what we're going to do, now we've already got at least probably 2 or 3 marks for that. We need to talk about how to vary the length and then what we do afterwards. So we're going to say vary the length because that's what the question says as the wire length of the wire changes. So vary the length by basically moving the crocodile clips. So you don't need to say exactly how much by, but we could say by 10 centimeters or something like that. Because we don't have any results here. By 10 centimeters. And then because we mentioned this here, we could then say repeat the same measurements, so current and PD measurements, and calculate the new resistance, or calculate resistance for basically different lengths of wire. They want in your answer an indication that you have, so I'm just going to write different lengths of wire up here. So I'm running out of room. They want indication that you have got the idea that you're changing the length, you're measuring the resistance. So change the length of wire. Now, as always with these kind of methods, you need to try and mention how to be a good scientist as much as possible. So we could talk about things like repeat the whole thing. So repeat for all lengths, and then things like remove any anomalies. So results that don't fit the pattern, we remove them before calculating a mean. I don't know why I'm quite going off the end of this paper here, but I am. And that would actually be fine. You could also talk about, to make it a really good experiment, so disconnect the circuit between readings to stop it getting hot, something like that, to prevent the wire overheating. My writing's getting really bad here. And that would be absolutely fine. Like I said, that's probably too much information. That will be both a safety thing, but also a method that ensures its accuracy. Next, what relationship are we looking for? Well, the longer the length of wire, the higher the resistance. The idea is that if you've got a length of wire that's twice as long as another piece of wire, if you're an electron trying to get through, it's just going to take you twice as long. So if we measure the current, the rate of flow of charge, they're not going to have as many going through per second, the longer wire versus the shorter wire. So it's this graph here. Let's finish off this question. So we've got a question all about sort of the hazard of a cell that's got a potential difference of 1.5 volts. Why wasn't it electrical hazard? The answer is actually quite obvious here. So we've got to talk about basically 1.5 volts is not that high. Generally speaking, to have any sort of electric shock, you need to talk about hundreds of volts or thousands of volts. So PD is very low, so therefore there's a low risk of electric shock or electrocution or something like that. You can't just say shock, you'd have to say electric shock here to get your marks. Question 4, we've got a question that's going to be all about static electricity. So again, this is going to be for separate science students only. And it's got a Van de Graaff generator, which you might have seen in class before. You're not technically really supposed to use them that much in class anymore, because they can be a bit dangerous if you've got a pacemaker or a heart murmur or something like that. But this is what it is. I'll explain what happens. So you've got a rubber belt that moves up and down, connected to a motor. Because it's moving up and down, it's got quite high friction. Inside the metal dome, electrons are transferred, and means that basically this thing here has a charge. You don't necessarily need to know that for this question. It will explain on the other side, but that's roughly what's going on. Now, on the other side, we've got a very famous woman who's got some, well, she's famous because she's in an exam paper, her hair standing up on end, basically explaining why that happens. So with anything that's to do with static electricity, it's all about electrons that are moving. But we have got to figure out here which way they're moving and like why do they cause their hair to stand up on end. Okay, so first of all, it says the dome is negatively charged. So if you have a look back at our diagram, if the dome is negatively charged, that is important because it means that if someone touches it, so if someone's hand touches the dome, they're also going to get a negative charge from it. So what we say first of all, how do we get a negative charge? Well, it's because electrons that are negative get transferred to the person or to the woman or to the student. Then we say, well, how does that make things stand up on end? Well, if you imagine the student has now got a negative charge all the way through, so the dome's got a negative charge, the student's now got a negative charge, that means the hair has also got a negative charge. Now, what do we know if someone's hair is negative and something near them is negative? Well, two negatives repel, like charges repel. So what we'd say something is that the hair is negatively charged. So if the two things are negative, they're going to repel. So like charges or two negatives repel. So the hair moves away from the person, something like that. And questions to do with static electricity always have a similar format. You've always got to talk about electrons being transferred, what the charge is it positive, negative if we know, and then is there going to be some sort of repelling or attracting happening there as well. 4.2, an electric field, and this caught a lot of people out. This is a really poorly answered question. This is the kind of question where it's in the specification what the definition is. It might not be in all revision guides, so you've got to learn this stuff like word perfect, be really thorough. An electric field, the definition is a region or an area around a charge or around a charged object where another charge or another charged object experiences a force. So the idea is if you are close to a charged object, then you'll experience a force from it. If you're not, then you won't, because it has an electric field around it. How does the electric field strength vary as the distance from the charged metal dome increases? Well, I was just trying to draw it up here. If we've got distance versus electric field strength, the idea is that if you've got further away, there are less field lines per centimetre, or there's less dense field lines, so therefore it just decreases. It gets weaker the further away you get. Okay, next we've got another equation question. This time we are going to have to do a bit of rearranging, so I'll show you how best to do that. So we've got a conductor moving towards the dome, and that's kind of it. We don't need to know much more than that for the minute. It says it transfers an amount of energy, and we've got an amount of charge. We're trying to find a potential difference. So let's look at our equation sheet, and if we look down here at the bottom, we've got energy equals charge times PD, so we're going to use that equation. So I'm going to introduce to you, if you don't know it already, a method called FIFA. There are lots of different versions of it as well, but for any equation question, I thoroughly recommend using them, especially if it's one where you might have to rearrange towards the end. So F stands for formula. So the formula we're going to use is the one I just showed you, energy equals charge times PD. I stands for insert values. Now, before you do any triangles, I don't think you should do triangles personally. Before you do any sort of rearranging, let's insert our values, because that's what the first mark is for on AQA mark schemes, and it also helps you figure out what else is going to happen. So we've got two, and this little symbol here we need to know, this is called a microcoulomb. So micro is one of those prefixes we need to know. That's 10 to the power minus 6, or it's a millionth of a coulomb. So if I've got two of them, my charge is now 2 times 10 to the power minus 6. And like I said, that's a mark automatically for doing that, and it's a mark for putting our numbers into our equation. Next, what we're going to do is figure out whether to times or divide. That's where F comes in. That's for fine tuning, means basically how do I find out what V is. So I'm going to keep the equal sign in the same place. I've currently got this value here times by V. So to get V by itself, I'm going to have to divide both sides by 2 times 10 to the power 6. So if I divide it from the right side, it cancels, it disappears. From the left side, I'm left with this calculation here. I'm going to leave it all in brackets to make sure I use them again later on my calculator. If we put that into our calculators to get a final answer, we'll get V equals 300,000 volts, which is what our potential difference is. If you didn't do the conversion properly, if your answer starts with a V and you've got some valid workings, you just missed out this bit here, you'll get 3 out of 4. If your answer, let's say, was 3,000 or 3, if you didn't do your workings clearly, you're not going to get those sympathy marks, and make sure you show your workings out really, really clearly. Next one, which of the following changes was increase the distance a spark can jump between a dome and a conductor. So for a spark, we need to have a less resistance, basically. So we decrease the electrical resistance of the air. We could do it with a higher field strength. We could do it with an increased charge. We could do it with higher potential difference, but these all say decrease. So the only decrease that would be worth a mark there is 4.5. It's the electrical resistance, and that's the answer for 4.5. Okay, we're really starting to motor through now through the electricity questions. This one is really standard type question. You should have a flashcard on this or something similar to make sure you're getting the marks. The frequency and PD of the main supply, it just happens to be 50 hertz. These are just numbers you need to know. And the potential difference in the UK is 230. Next one over here, we've got the resistance of a coin. And let's just highlight the numbers we've got. Again, we've got power, we've got current, and we're trying to find resistance. So an equation that might be useful, again, it's on the first side of the sheet. It's going to be this one down here. There's only one with power, current, and resistance in, which is power equals I squared times by I. So let's then write down our equation. I'm going to do FIFA again. I know some of you might be really good at this already, but just to make sure we're getting our marks. Now, first is our formula, P equals I squared times by R. Next is insert values. Before we do that, we can see we've got another little prefix in. Now, this one is a little m, which I know is really confusing because it's different to a big M. This stands for milli, and milli is 1,000th or 10 to the power minus 3. So we've then got to work out 340 times 10 to the power minus 3 before we put in our calculation. So I'm just going to do this bit up here because I think it makes it easier later on. 340 times by 10 to the power minus 3 actually equals 0.340. So that's what I'm going to put down here because I've done my conversion already for that first mark. So 0.34 or 340 equals the current, which we have 0.75 squared times by the resistance. That's another mark. Then we're going to do some rearranging. So I'm going to divide both sides by 0.75 squared. You could do this bit first if you wanted to, or just leave it in the squared form to do in your final calculation. And if we do all that, so final mark for rearranging, and if you do that calculation, R would equal 0.60 or 0.6 ohms as the resistance. This is a very random question down here. Coins that are dirty are not recognised by this vending machine. So just one reason why. There's a few different ways of saying it. Recognise, I think, is a bit misleading here, but essentially for the vending machine to work, it gives you a clue up here. It says it measures the resistance of the coin. Now, if they're dirty, they're not all made of coin, they're made of dirt as well. So you could say something like the dirt changes or increases the resistance of the coin. You could also say, for Mark in this question, it doesn't match the resistance of a known coin, or it stops charge flowing, it stops the current, that kind of thing. But here's a clue up here because they mentioned it earlier in the question. I would always go with that if you get a chance to. Next, we've got a circuit symbol. Another thing you just need to know, this is a thermistor. So the symbol for a thermistor, good things to memorize, is it's a box. It is probably the hardest symbol, I'd say, to memorize. It's got like a hockey stick going through it like that. The way to remember it is, it kind of looks a bit, if you squint a bit, it looks like a backwards T. So T for thermistor, that's what that one looks like. Next though, this is an insanely hard question, I think. It's kind of a little bit of A-level physics, but they break it down enough that you can do it at GCSE, but you're just applying knowledge and you're applying a couple of equations and you've also got a graph. You know it's hard because it's 5 marks and it's a calculation question. So it tells you a cooling system inside the vending machine turns on when the temperature is above 20 degrees. We're after the potential difference when that happens. Now, this graph does not tell us potential difference, but we do have it here, so let's use it first of all. So let me get a ruler so I can use it for you guys. So first step is to draw a line up from 20 degrees So 20 degrees goes up here. What is the resistance when we get to that point? Resistance is 4 big squares up between 0 and 100. So that's going to be 80 ohms. So that's our first stage. So 80 ohms is what's going to be the value of this resistor here. We know this one's 400. This one we know is now 80. So the first step to work out potential difference across the thermistor is to figure out, well, what equation could I use for that? Now you might be able to figure out V equals I times R to be able to figure out the potential difference. Now I know the resistance. I need to find out this. I need to know what the current is in the circuit. So the total current in the circuit, or the current throughout the whole circuit, which is, because it's a series circuit, it's the same. We can work out that by doing this equation again. So I'm going to go a bit slowly here because I think this is, like I said, quite tricky. V equals I times R. So the current in the whole circuit, we know potential difference. That's easy because that's 12 volts. Current we don't know. But the total resistance, now that I know this is 80, the total resistance is 480 or 400 plus 80 ohms. So now I've got those numbers, I can work out the total current in the circuit. So I've got to get rid of the times by 480, so I'm going to divide by 480. So if I do that nice and carefully, I'll therefore get the current is 0.025 amps. Now that's, I think, 3 of my 5 marks already, definitely 2, yeah, I think 3, which is quite nice. However, we haven't worked out the potential difference yet. So the potential difference in the thermistor, we're going to use V equals IR again. That's why this question is tricky, because we've got the same equation twice. V equals I times by R, but now we know what the current is, because the current is the same everywhere, and we know the resistance across the thermistor is 80. So it's just a matter of plugging those numbers in. So 0.025 times by 80, which will give us an answer of 2 volts or 2.0 volts. So quite a quick, tricky question. There are a couple of other ways of doing it as well. You could do ratios, but this is the way you'd learn it at GCSE, by using these different equations. My top tips are, get your marks easily. Just use an equation with something you know is true, but you've also got to use the information earlier in the question. So you've got to be able to figure out, what is this total circuit? How would I be able to get my graph value into there as well? Okay, question 6, we've got another big long calculation. This one's a lot more standard. But first of all, we've got to talk about an energy store, which one increases as the bungee cords are stretched. So the bungee cords get stretched down, then release. We should know that's elastic potential energy. You need to mention the word potential here. It's not just elastic energy, it's potential energy for the full mark. So next one, this is what's known as a multi-step calculation. So if you're doing a higher tier physics paper of either combined science or separate science, you will always get one of these in each paper. We have done since, I don't know, 2016, 2017. So we're going to need to use 2 equations. So 2 equations to be able to get our answer. How do we know that it's one of these equations? Well, it's 6 marks for an answer. There's no unit, there's no conversions, there's no standard form. So we're going to have to use 2 of them because it's 6 marks here. So first of all, let's just have a look at the equation sheet and write down any equations that might be useful. So we've got, let me highlight all the things we've got in the value. We've got spring constant, which is a bit of an unusual one at paper 1. We've got mass, we've got gravitational field strength G, which on account of maximum height, and we've also got some extension. So one of the equations to use should be relatively straightforward. There's only one in paper 1 that's got spring constant in it. That's this one here. So let's write down that one straight away. So elastic potential energy equals half times by K times by extension squared. Next we've got to use mass and gravitational field strength and height, and it's actually handy, it's the one below that. So the second equation we're going to use is the gravitational potential energy, mg times by h. So let's use this one first, and then we've got to do a bit of rearranging later on. So this should be one thing, even if you don't know that that's the next equation, just work something out correctly. You're guaranteed to get yourself at least 2 or 3 marks. So elastic potential energy is going to be half times by spring constant, 735, times by the extension, which is 8. Now we don't double this because there's 2 chords. I'll tell you why a bit later. But if you put all those values in, you'll get the elastic potential energy is 23,520 joules. Now we don't double the extension here because the extension of each one is only ever 8. So the extension of the chords, it goes 8 meters down, or sorry, 8 meters along here. It doesn't get doubled, it's just there's 2 of them. So what we end up doing is we do 2 times the elastic potential energy because there's 2 chords. So times by 2 because there's 2 bungee cords. So times by 2 equals 47,040 joules. Make sure that's clear what you're doing somewhere in your answer. Next, we're going to work out, so we've got 2 marks there and the third mark for doing that, the height. So what we're going to say is that all the elastic potential energy, when it gets released, gets converted to, so I should say elastic potential energy here, gets converted to gravitational potential. So elastic gets converted to gravitational. Obviously not all of it will get converted, but if you don't have any information about friction or air resistance, then we can assume 100% of it gets converted. So now we can use this equation and we can say, I'm just going to put this down this side here, we can say that the elastic potential energy is going to be the same as the gravitational, or gravitational is going to be the same as the elastic. So I've got this is my EP, mass we get given is 240, G is 9.8, and H we don't know, so we've got to leave that blank or leave the letter in there for now. So let's then work out what this is going to be. So 47,040. We've got to get rid of these two numbers here. So I'm going to divide them on this side of the equation. You could do an extra step to work out what they are together if you wanted to. If I do that calculation together, I'll get height as being 20 meters. If you got 10 or if you got 40, you might have doubled the extension before you needed to. But you need to double the energy, not the extension. Next, the actual maximum height, as we just talked about, it will be not quite as much as that value because not all the energy gets transferred. So we'd say basically not all or not 100% of the elastic potential energy is transferred was converted to gravitational potential energy. And the reason for that is because there it gets transferred to other forms of energy. Now, those forms of energy we should know due to air resistance and friction, but not in this case, it's just air resistance. So we'd say due to air resistance, like opposing the motion of the pod. So therefore it gets transferred to thermal energy instead. So if there's air resistance, there's always going to be some thermal energy involved. So not 100% of it gets converted, and then that's due to air resistance there for your second mark for that question. Next, let's move on to a practical question. So this question's got a measuring cylinder in it. It's not really part of a required practical, but it kind of is a bit of part of the density one. But we're not going to write a method, we're just going to analyse it. So it shows the volume of a metal ring, and the question asks, when measuring the volume, student's eye was in line with the water. So that means like there. What type of error would have been caused if they weren't? Now, there's different types of errors. It's only ever the answer is either going to be random or systematic, or zero error is a type of systematic error. In this question, it's going to be a random error. Now, if they weren't in line with the level of the water, the idea is when measuring the volume, it should be, but if the student makes a mistake and measures it from here and they're looking upwards at it, it's only going to affect one reading, or only going to affect that reading. It's not going to affect all the other ones. Usually, if we talk about random errors, it's almost always caused by a human. We don't say human error, but that's the kind of thing we mean. Systematic error affects all the readings and is usually something to do with equipment or method that would affect all your results. Next, we're going to talk about up here, the student tied a thick piece of string to the metal, so they should have used thin string instead. The idea is that the thin string doesn't affect the volume measurement as much as the thick string. So we'd say something like the thick string would affect the volume measurement more. It would actually increase it. It's only 1 mark, so it would increase the volume we measure, but we could say affects the volume measurement more is absolutely fine here. Next, we've got some values of the volume that's measured by this process, and it says the true volume, or the actual volume of the ring, was 0.44. Then it says, even without using the string, the measuring cylinder could not give an accurate value, and the reason is up to these results here. So if we look at the volume of the ring, the measurement is 0.4, the actual value is 0.44. So if we look at the measuring cylinder again, there's a clue there as to why we couldn't use that, which is that the only measurements you could get from this would be, for example, 2.1 or 5.6. It only measures to 1 decimal place because there's only 10 intervals between these two values. So 0.44 would be somewhere down, 0.4 would be somewhere down here. It cannot measure to an extra decimal place because that's the resolution of the equipment. So we'd say something like the resolution of the measuring cylinder, that's the smallest thing it can measure, what we were just talking about. Measuring cylinder is 0.2 centimeter cubed. You could also say it can't measure 2 decimal places, You can't just talk about how measuring with enough decimal places. You've got to be specific, so it can't measure 2 dp. But this is probably the best answer. I'd say you talk about resolution. Next, we say they tried to measure the mass of the ring. The ring was removed from the balance. The reading on the balance with nothing on it was 0.02 grams. How could the student use the readings from the balance to determine the correct reading? This is an example we called a zero error. So ideally, you wouldn't want to have this. Ideally, you would zero the scale, so they measured 0 when they should read 0. However, this person hasn't done that. So what we could do is basically say they could subtract or take away that value, which it was out by 0.2 grams from every reading. So not from just one reading, but from each reading. And that's what I mean when I talk about systematic error. Zero error is an example of a systematic error. It's a problem with the equipment and it affects every reading. So to adjust for it, you've got to do something that affects every reading as well. Next, we've got an equation question, and we've got some density value, we've got a volume value, and we're trying to work out the mass of the ring. However, we need to be really careful here. We've got the density given in kilograms per meter cubed. We've got this in centimeter cubed. So we do need to convert that to meters cubed to be able to get full marks for this question. So what we'd end up doing is we'd say, obviously set out our FIFA method again. So formula, insert values, fine tune answer. So our formula is density, this symbol here, which you can just write out in words if you want to, equals mass over volume. And the mass is what we're trying to find out. We do know the density, 21500. With mass, we're trying to find out the volume. Like I said, we can't just leave it in centimeter cubes. We need to convert it into meters cubed. So how do we do that? It's not as easy as just saying divide by 100, because there are 100 centimeter cubes. 100 centimeters in a meter. We can't just divide by 100 because it's cubed. If you imagine a box like this. If you imagine I've got like 1 centimeter here, that's the same thing. So 1 centimeter cubed as saying 0.01 meters on each side. So we have to find the volume, 0.01 times 0.01 times by 0.01. So the idea is that's going to equal, so 1 centimeter cubed is going to equal, if you times all those together in your calculator, that's going to equal 1 times 10 to the power minus 6 meters cubed, or 0.000001 meters cubed. So how we convert from centimeter to meter cubed is we times by 10 to the power minus 6. The other way of thinking about it is you divide by 100 and then you do that 3 times because it's cubed. It's the same value. Okay, so about 3 different ways of looking at it, just one conversion, but either of those would give you the right answer here. So what we do is we do 0.44 and we do times by 10 to the power minus 6 in our equation. Next, after that, it should be relatively straightforward. If you didn't do that stage, you will just lose 1 mark as long as your workings are clear for the rest of it. This time we've got divide by something, so to get rid of a divide, we've got a times. So I've not left rows of room here, but we times both sides by this value here. And then if you put all your values in for the mass, you should find the mass is equal to, it's quite a small value, but it's 0.00946. The reason that's nothing to be that afraid of, you could put in standard form if you want to, is that even though it's small, it's a tiny little ring that goes into a water. It's not going to be a kilogram, about, let's go about a thousandth of, well, 100th of one of those. It's not too far off. Let's move on to question 8, which is a question all about pressure. Really, really common, really standard type of question, this. So we've got a syringe with a plunger, which could be used to move in and out. It says when the plunger was pushed slowly into the syringe, the pressure increased. So we don't get marks for saying that, but we do need to explain why the pressure increased, and the temperature doesn't change. So pressure, if we didn't know, whenever we talk about gas pressure, it's all about particles colliding into the walls of their container. So particles move around randomly. When they hit a wall, they exert a force, which is where the pressure comes from. So the idea is when you push the plunger in further, is that the particles, first of all, there's a smaller volume, but we need to say the particles are closer together. Or you can say there's less particles per square meter or something like that. And if there's less particles closer together, that means there's going to be a greater frequency of collisions. So when we talk about colliding with the wall, if there's a greater frequency of collisions, that's because there's more particles in a certain space, or they're closer together. Collisions between, this isn't between particles, this is between the particles and the wall and the container of the syringe. Okay, This word frequency is super, super, super important. You can't just say greater number of collisions. You could say greater rate of collisions. It's got to be something per second, because you could have infinite like time and therefore be loads more collisions. Greater frequency or greater per second is what we're talking about there. So when that happens, as we mentioned earlier, particle hits a container, comes back out, there's going to be a greater force that acts overall because there's more of these collisions per second exerted on also a smaller area. So the idea is it's a smaller area because there's less space. So you've got a smaller volume you're working with. If the plunger's gone into there, there's a lower area. Now on your equation sheet, this can be helpful. It's kind of more of a paper 2 thing, but pressure equals force divided by area. So you can always use that to help you out with the definition here, because that's what pressure is. You don't get marks for saying that, but pressure equals force per unit area. Next, we've got a type of syringe that could be used to start fires. Now, starting fires is not massively relevant here, but it also to do with the increase in temperature that allows us to start the fires. So how does increase in temperature affect air particles? The idea is that the temperature is all to do with the particles' kinetic energy. So how much they're moving or how much they're vibrating, I should do arrows here, not vibrations, is to do with their kinetic energy, which is their temperature. And last bit here, we've got a calculation with specific heat capacity in it. There's only one equation that's got specific heat capacity in it, which is quite nice. So let's write down our equation. We're trying to work out temperature change. We've got mass and we've got energy. So the formula we've got is on your equation sheet: energy equals mass times by specific heat capacity times by this weird looking symbol is change in temperature. So before we insert our values, let's do a conversion. Let's check through. Now, kilograms should stay as kilograms, but however, specific heat capacity should normally be in joules per kilogram. It's a really tricky one to spot, this one. It's in kilojoules per kilogram. So therefore, instead of 1.01, it's a kilo, so times by 1,000 gives you 1010, and that's now in joules per kilogram degrees Celsius. So we can now use that in our answer. So the energy, let's just insert our values, 0.0130. The mass, nice and easy, but it's in standard form, just use a scientific calculator. And specific heat capacity we now know is 1010. Mark for doing that, mark for setting it up. Next, to work out the temperature change, we've then got to divide. So we've currently got, I missed out the specific heat capacity. There we go. Specific heat capacity C times by this. Sorry, it looks messy. We've got to divide this side by both of these sides here. Now I'm just going to take an extra step here, just because you can always take an extra step. And mine looks quite messy, so you can need to out a bit. I'm going to times these two together here, just to make life a little bit easier. You don't have to do this if you're happy just doing it all in one load like I did earlier. That's fine. But if I times this by this, I'm going to find 2.626 times 10 to the minus 5. And now that's times by C, the thing we're trying to find. I'm being an absolute mess of this. Sorry, temperature, that is. There we go, change in temperature. There we go. So times by the temperature, which we're trying to find. Now we've got something times that. It's just a regular old equation now. So for our answer, we've got to fine tune. We've got to divide this by this. So 0.0130 divided by 2.626 times 10 to the minus 5 will give us our temperature change. And that, if you put into a calculator, is 495 degrees Celsius. It's quite a big temperature change, this one, so it might catch some people out. However, it's something catching a fire, and it's just at room temperature, so to catch fire, something has to be pretty hot. So that's your clue that this might be all we need for our marks. Let's have a look at a radioactivity question. We've managed to get the whole paper so far without radioactivity. We've got a little experiment here. You might have seen something similar to this in class. We've got a detector, we've got a radioactivity source, and we've got a counter that's measuring the counts per minute. Usually it's just per second, but per minute could also be another way of saying it. The question says, how do we show only emits alpha radiation? So let's have a look at some key facts of alpha radiation first that can help us out. So alpha radiation, there's no materials here, so we just got to talk about the range. There's only air between the detector and the source, so it only travels a few centimeters in air. Beta, on the other hand, travels a lot further. So let's then try and put this into an answer. So the idea is that the radiation from the source in the question only travels, and we could be specific here. Let's look at the graph. It goes down to 0, or not close to 0, after about 3 centimeters. So source A only travels 3 centimeters, and then it doesn't go to 0. I almost made that mistake there myself. You see it's a bit above the line, so it only travels 3 centimeters before decreasing to background radiation, or before the count rate decreases to background radiation. Now I'm going to put that word in here. I'm going to say before the count rate decreases back to background radiation, because obviously it's not the radiation itself. And I can't spell. There we go. All right. So now we've said that, we just get a mark for saying, that's probably the easier mark on the paper, is to say we know alpha has a very short range. You could say a few centimeters if you wanted to, short range, a few centimeters in air. So it must be alpha, basically. Now, you actually don't need to talk about beta here. You could talk about, if you wanted to, you could say beta goes around about a meter, gamma goes really much longer. You'd have to be really specific with your answers, but I think it's just easier to talk about alpha here, to be honest with you. The next one we're going to talk about if source B emits alpha, beta or gamma. Now we don't really know, because if we increase it a lot, obviously it's decreasing, but we haven't got enough information, we haven't got a big enough distance. The question doesn't worry too much about the graph though. It says what absorbing material could be used to show which type of radiation is emitted. Now absorbing material, we should know that graph. We've got that paper, we've got that aluminium, we've got a big lead block. Alpha gets stopped by paper, beta gets through to aluminium, gamma kind of keeps going regardless. So an absorbing material, we'd say use a sheet of aluminium or aluminium sheet. Now be careful, you can't just say aluminium here. It has to be a sheet or foil or something like that, because it has to be quite thin. So thin aluminium. So we use that and we'd say that beta will not penetrate or not get through, but gamma will. So the idea is if the reading doesn't go down by much, then you know it's gamma. If it goes down by loads and was to background radiation, you know it's going to be beta because it's been absorbed. One precaution or safety precaution the teacher could use, relatively straightforward here. So precaution to reduce the dose, so the dose they receive. So you could say increase the distance between the source and the person, between them and the source. You could say you do that by using tongs. You could say limit exposure time. You could say wear a lead apron, keep it in a box, point it away from people. Like even just say using tongs is absolutely fine. Don't say use like hazmat suits, things like that. That won't help. The teacher could say to avoid becoming contaminated. So that means for it to get inside their system. So the easy way to talk about that is to wear gloves. Or you could talk about tongs again, which is a bit silly. I'm not saying the same thing twice. But to stop it getting in your system, both of those would be valid. Right, the worst answer question on possibly, I think, the whole paper is this one here. It talks about activity. We've got a graph of number of atoms and how they decay over time. Usually this kind of graph you look at for half-life, well, not here. It says the activity is the rate at which a source decays, or unstable nuclei decays. Determine the activity at 300 seconds. So it's basically the change in the number of nuclei divided by the change in time. Whenever we've got a change in time, we'll talk about rate, and this applies for like chemistry and biology as well. If it's a curved line, we have to draw a tangent. If it was a straight line, I'd just measure the gradient, but because it's a curve, we have to draw a tangent. And the mark scheme is really specific here, really clear. You cannot get any marks for the first three unless you draw a tangent. You can't just do like a quick gradient calculation. So don't be generous to yourself here. If you didn't know it's a tangent, learn from it, but move on. Next, we're going to actually draw the tangent on. So do a little point at 300 seconds for a tangent, just like in maths if you're drawing them. It should be symmetrical on both sides of it. So I'm going to draw mine about here, I'm going to say. Maybe a tiny bit steeper. There we go. And the idea is once you've drawn this on, you need to actually draw it on. You then measure the gradient of this line. So I'm going to do it nice and big because it's easier to measure gradients like that. So my triangle goes all the way down to here. So when I'm working out the gradient, I have to be really careful. The y-axis is times 10 to the 23. But first mark for tangent, next mark for working out the gradient. So gradient is going to be equal to obviously change in y over change in x. So for mine, I've gone from 3 to, that's 4, 0.3 to 4.9. So therefore that's going to be 4.6. That's how big mine is. Next, I go from 0, and for that to take place, that's 640 seconds. So I'm just going to write these down here, so I've got them. So that's going to be, for me, 4.6 divided by 640 seconds. I did say earlier, I almost forgot about it then, this is times 10 to the power 23, so that's your sort of fourth mark in this question, which is a bit sneaky. So let's put all those values in and see what we get. So 46 times 10 to the 23 divided by 640. For me, that gives me 7.1875. times 10 to the 20, which I can round if I want to. There's quite a big range for this one because drawing a tangent is kind of quite tricky. I think the range is between 6.5 and 7.5 times 10 to the 20, basically. The unit is becquerels and BQ, so you get a standalone mark for doing that as well in this question. Okay, question 10, let's move on. I think it's the last one. Yep, it's the last one, another electricity one, just to round off everything. And this is a really good lesson, just because it's the last question. This question is really nice, I think. There's a couple of equations here. You've got like a bit of wiring inside a plug. You've got a symbol equation. So don't always leave the last question till the end. It is perfectly fine to leave alone some questions earlier in the paper and then do the ones towards the end first and then come back to the hard ones later, because otherwise you'll miss out easy marks here. Like I said, I think these two questions especially are really nice. You've probably revised these. So the insulation covering the live wire, we need to know the live wire is brown, neutral wire is blue, earth wire is yellow and green. That's just an easy mark. Circle symbol for a fuse. We've got two symbols in this part of it. Part of the paper. It kind of looks like the fuse itself. We've got a metal wire goes through the whole of the symbol. If it's just a box, it's a resistor. A fuse means it's got a wire going straight through it. Next, we've got a calculation where we've got current we're trying to find. We've got charge flow. We've got a time. This is time, even though it might not look like it. So we're going to do charge equals current times by time. And we have got a conversion as well. So let's do that first before we dive in. This is ms. So s is seconds. It's not meters per second, S is seconds. So milli is just like, I think it came up earlier in the paper, 10 to the power minus 3. So 400 milliseconds equals 400 divided by 1,000 or times 10 to the minus 3 seconds, which I'm just going to write down here, 0.4 seconds. We can put it in our calculation. So charge is 2, that's nice and easy. Current we're trying to find, I'll leave that as an I, or I could write an X. This is 0.4. Then the calculation comes relatively straightforward. We've done lots of these already in the paper. Make sure you know how to do these. To get rid of a times 0.4, we divide, and therefore the current is going to equal 5 amps, 5.0 amps. So we write that in our answer line for our fourth mark. Next one, we've got to do with latent heat. The fuse melts. The equation sheet we're going to use, we're trying to find the mass. We've got latent heat here, and we've got the energy used to melt the wire. The only equation we could use is energy equals. The only one that's got latent heat in is mass times by latent heat. Now, this is again in kilojoules, and it's calling out twice in one paper, kilojoules per kilogram. Kilojoules shouldn't be in kilojoules, it should be in regular joules. So we times by 1,000 to get into regular joules, so that's 60,000 joules per kilogram. Then we can use it. So I'm going to treat myself to not actually writing FIFA for this one, which is going to write down our values. So mass times by latent heat. And then even though it's going to be a really small number, it's a mass of a fuse wire. It's not going to be that high. It's definitely not going to be as high as a kilogram. We divide by 60,000 to get our final answer for the mass, which is, like I said, really small. But it's not a problem because it's a really small, light piece of equipment. So mark for the conversion, mark for subbing in the values, mark for answer, and there's 4 marks. And to finish off the whole paper, it says it assumes there's no energy transfer to the surroundings. How would the time taken for the wire to melt be affected if some energy does get transferred to the surroundings? So when you think a bit more carefully here, now the wire is melting, so therefore it takes a certain amount of energy for that to happen. If we say that the time taken, what happens to the time taken if someone's transferred to the surroundings, the amount of energy that gets transferred would be lower because someone's getting lost to the surroundings. So actually it would mean it takes a longer amount of time, and the reason is you need to say more energy needs to be transferred or is transferred to the wire or to the fuse wire. Now, please be careful with this one. You can't just get a mark for saying more energy gets transferred to surroundings because it already tells you that in the question. It's not wrong, but they tell you that in the question, so you can't get a mark for it. So therefore, you need to say more needs to be transferred in total for that to happen. And there we go, there's the end of the paper. If you missed anything, use the timestamps to go back, and definitely make sure you're really thorough with your marking, okay? You need to be as honest and as accurate as you can, and learn from every single past paper question you do. Hope you found that useful though. Please check out my video for any other videos to do with GCSE or A-level physics.